The plan for this lesson is to discuss the central tendency measures, namely, we will go over the mean, median, and mode. In practice, to make the most informed decisions, one should look at summaries of any available data. Here's an overly simplified example to make a point. So before registering for a class like CS412, it's reasonable to ask what was the average last year. So an average of 90 is assuring, but an average of 67 is a little bit concerning. So although we don't know the whole grades distribution, still the average is a good starting point. But there is always going to be a difference between what we call the sample mean and the population mean. So let's break down these concepts. In our simplified scenario, the population mean would be the average of all students who have ever taken this class. So if this class has been running for the past 20 years, then I need to find the average of all the students in those 20 years, which is an information very hard to get. Instead, we can rely on the sample mean, maybe finding a sample of 50 students and compute x bar, which is the sample mean, and hope that x bar is somehow close to mu. The weighted arithmetic mean, some samples are given more weight or less weights than other. Typically, weights are equal to 1, then we are back to the computation from the previous slide. The trimmed mean is often used in practical situations. A very famous example is sport judging, when a number of judges give scores and they drop the highest and the lowest, then they compute the mean. Another example would be if we want to compute the mean salary in this university, it would make sense to drop the highest earners like the basketball coach and the football coach. One issue with the mean as a central tendency measure is it's very sensitive to outliers. So large values are going to skew the mean value. The median is the middle value of a number of values, and it's a better measure, and it's more robust. The advantage of the median is that now we are looking at the orders of the value, not at the center value. In the following example, we are going to learn how to estimate the median by interpolation. Very often, we are presented with a histogram that summarizes the intervals and their frequencies, and we want to use this information to estimate the median. As a first step, I need to identify the bin where the median value is located. We already know that there are 403 samples and the median location is the 202, but where is 202 inside this histogram? The cumulative frequencies is going to help us to answer this question. So starting from the leftmost bin, we have 36, then 36 plus 54 is 90, plus 69 is 159, and so on. So now it becomes clear that the location of 202 falls inside the bin of 25 to 30. The next step is estimating the median. All what we know so far is that the median should be somewhere between 25 to 30. So if I want to compose these formulas, I should have 25 plus something. And this something should be the interval width multiplied by a ratio. So if this ratio is 0, get 25. If this ratio is 1, I'm going to get 30. And the ratio is going to tell me where inside the bin the median is located. Is it in the first 10%, 50%, 90%? And then I multiply it by the bin width. So in this very example, it translates to 202, which is n over 2, subtracted by the cumulative frequencies at the beginning of the bin, then divided over the frequency at this bin. This frequency, I believe it's going to be maybe 52-ish, and then you multiply it by 5 and end up with 27.62. The mode in a distribution is the value that occurs most frequently. Empirically speaking, and referencing this right skewed distribution, we can note that the mode is smaller than the median and the mean is larger than the median, which kinds of explain the empirical formula, which states that the difference between the mean and the mode is 3 times the difference between the mean and the median. This empirical formula seems to hold for slightly skewed distributions. These are density functions. A bimodal function is a distribution or function with 2 distinct peaks or modes. Similarly, we can have a trimodal function. Symmetric data is when the mean, median, and mode are all overlap at the same point. Distributions can be positively skewed, which means the mode is less than the median and the median is less than the mean. So in other words, the right tail is extended. And on the other hand, a distribution is negatively skewed when the left tail is extended towards the left, which means that the mode is greater than the median and the mean. In summary, we gained insights into the data by computing the central tendency measures, which are the mean, median, and mode.